Hi there, Mr. Sutton here, bringing you the AB Calculus 5-6 homework solutions on trapezoidal rule. For this problem, we're trying to approximate the area under negative x plus 3 from negative 6 to 2 for subintervals using trapezoidal rule. We'll start with a table. So in this table, I'm going to be putting my x values. We're going to start at negative 6, and 4 subintervals over this interval here means that we have to go by 2's. So negative 4, negative 2, 0, and 2. And now let's get the y values that go with that. We're going to have 6 plus 3 is 9, 4 plus 3 is 7, 2 plus 3 is 5, 0 plus 3 is 3, and negative 2 plus 3 is 1. Next, we're going to set up our trapezoidal areas. So for the first one, we're going to have 9 plus 7 over 2 times a base of 2. And this is approximately equals here. Next, we're going to have 7 plus 5 over 2 times a base of 2. And then 5 plus 3 over 2 times a base of 2. And then 3 plus 1 over 2 times a base of 2. So you could leave it like this if it were a free response problem. If you need to simplify it, all these 2's are going to cancel out. So you really end up with 16 plus 12 plus 8 plus 4. And then that's going to be, let's see, 28, 36, 40. For this problem, we want to approximate the area under this curve using trapezoidal rule. We're going from negative 2 to 3 with 5 subintervals, so we can go by 1's. Let's set up our table here. We've got negative 2, negative 1, 0, 1, 2, and 3. So now for the y values, plugging in negative 2, we've got 4 plus 4 plus 3, that's 11. Plugging in negative 1, that's going to be 1 plus 2 plus 3, which is 6. 0 gives us 3 for an output. 1 is going to give us 2. 2 is going to give us 3. And 3 should give us 6. Let's see, we got 9 minus 6 plus 3. That is 6. Okay, setting up our trapezoidal areas, we've got 11 plus 6 over 2 times a base of 1. And all of these are going to be bases of 1. So we've got 6 plus 3 over 2 times 1. 3 plus 2 over 2 times 1. 2 plus 3 over 2 times 1, and 3 plus 6 over 2 times 1. Going through now, we've got, let's see here, this is going to be 8.5, 4.5, this is 2.5, another 2.5, and a 4.5. Adding all that up, this is going to be, we've got, let's see, 13 plus 5 is 18, and then we've got 22.5. For this problem, we're trying to approximate the area under this quadratic. So we're going to use trapezoidal rule, 4 subintervals from negative 2 to 2. On this interval, we can just go by 1's. So let's make a table now. We've got negative 2, negative 1, 0, 1, and 2. And now for the y values, this is going to be, let's see, negative 4 plus 12 is 8. This is negative 1 plus 12 is 11. This is just going to be 12. Now we've got, again, negative 1 plus 12, so 11, and then 8 for this output. So we're going to have bases of 1 for all these trapezoids. We've got 8 plus 11 over 2 times the base of 1. That's our first trapezoidal area. And now for the next one, we've got 11 plus 12 over 2 times 1, then 12 plus 11 over 2 times 1, and 11 plus 8 over 2 times 1. Going through and simplifying a little bit more, this is going to be, let's see here, this is 19 over 2, so that's going to be 9.5. This is going to be, let's see, 23 over 2, which is going to be 11.5, another 11.5, another 9.5. 9.5 and 11.5 is going to be 21. We've got 2 of those all together, so that's 42. On this problem, we need to approximate the integral from 0 to 9 of f of x using this table and the trapezoidal rule. So let's set up our areas. We've got an area of 0 plus negative 1 over 2 times a base of 1. Next, we've got negative 1 plus 0 over 2 times a base of, this is going to be 2 here. And we've got next 0 plus negative 1 over 2 times a base of 1. And negative 1 plus negative 2 over 2 times a base of 5 to go from 4 to 9. Simplifying a little bit more, This is going to be negative 0.5. And then over here, let's see, this initially comes out to negative 0.5 times 2 is negative 2. This will be negative 0.5, and this is going to be, let's see, this is negative 3 over 2, so that's 1.5 times 5 is negative 7.5. Adding all of this up, this is going to be negative 1.5, negative 2, negative 9.5 altogether. For this problem, we're trying to approximate this integral using this table and the trapezoidal rule. So setting up our first trapezoid, we've got 3 plus 2 over 2 times a base of 1. And notice I'm saying approximately equals, not equals equals, because this is an approximation. Next, we've got 2 plus 1 over 2 times a base of 3 from 1 to 4. And then 1 plus 0 over 2 times a base of 2. And then 0 plus negative 1 over 2 times a base of 4. Going through now, that's going to be 2.5. This is going to be, let's see, 1.5 times 3 is 4.5. This is, the 2's cancel, so just 1. And over here, 4 divided by 2 is 2, so that's negative 2 if you multiply it out. So we've got 2.5 and 4.5 is 7, plus 1 is 8, minus 2 is 6.
For number 6, we're trying to figure out if approximating this integral with the trapezoidal rule will give us an underestimate or overestimate. So in order to figure that out, we need to know the concavity of the original function over this interval. And we also need to know if it's the same concavity all the way across or if it's mixed. So let's take our second derivative now in order to get to that information. So first derivative, that's going to be, let's see here, we have a chain rule with a negative 2 tail. So that's going to be 6e to the negative 2x. And then going one more time for the second derivative, that's going to be negative 12e to the negative 2x. All right, so for concavity, let's test for critical values first of all. So if I set this equal to 0 and try to solve for x, well, there's no way you're ever going to be able to zero this out because it's an exponential function. So there are no critical values here, which means whatever the concavity is, it is the same everywhere. So I'm going to test out a value between 0 and negative 1, but honestly, you could plug in anything, and it should give you the same concavity. I'm going to try negative 1/2, that's right between there. If I plug in negative 1/2, or, well, anything here, this exponential term is always going to come out as a positive number. So really, it's just this negative 12 that makes the difference. So plugging in negative 1/2 or anything else is going to give us a negative second derivative. Since we are concave down because of this, that means that trapezoidal rule is going to underestimate. For number 7, we're trying to figure out if approximating this integral with trapezoidal rule will give us an under or overestimate. So we need to figure out the concavity of this function over this interval. Let's start with some derivatives. The first derivative is going to give us 8x to the negative 1/3. And then I need the second derivative for concavity, so let's do the power rule again. That's going to be negative 8 over 3x to the negative 4/3. And then I have to actually see if I have any critical values that are inside of this interval, just so I can make sure my concavity is consistent no matter what numbers I test in there. So setting this equal to 0, I've got negative 8 over 3, and this will be the cube root of x to the 4th. And, oops, yeah, don't forget there's a 3 down there. Won't actually make a difference for the critical values, but just for the sake of accuracy. So critical values on this, the only one we're going to get is 0, which makes this undefined. Since that critical value is not between the limits of integration, we don't have to worry about concavity switching. So let's just test any number between negative 1 and 4. So if I test, say, negative 2, whatever I plug in here, it's going to become positive after I raise it to the 4th. And then cube rooting, that won't make a difference. None of this will make a difference except that this positive value will have to be negative because of the negative that's always out here. So overall, f double prime of negative 2 is going to give us a negative answer, which means we are concave down on this interval, which means trapezoidal rule will under-approximate this one. For number 8, we have a continuous function on a closed interval given by the table above. And they're saying the trapezoidal approximation of the integral from 0 to 6 with 3 subintervals is going to come out to 52. Based off of that, we want the value of this mystery constant in our table here. Easiest way to do this is just set up a trapezoidal approximation of this and set it equal to 52. So let's go ahead and do that. We'll have 4 plus k over 2 times a subinterval length of 2 for our first trapezoidal area here. Next, we've got k plus 8 over 2 times the subinterval length of 2. And finally, we have 8 plus 12 over 2 times subinterval length of 2. And they said that that all comes out to 52. So equals 52. And this is one of those where I'm going to have to simplify a little bit because I'm actually trying to solve for k. So let me cancel out the 2's in these first two fractions and this last one. This last fraction we can just turn into a 20, 8 plus 12. That all equals 52. Next, combining like terms, we've got a 2k and 32 on the left side. Subtracting 32, that's going to be 20. And dividing that by 2, we get k value of 10. Choice D.
For this problem, we've got this shaded region from 1 to 2 under the graph of y equals x squared, and we want to approximate that area using the trapezoidal rule with divisions at x equals 4/3 and x equals 5/3. So using our trapezoidal rule, we've really got 4 x values in play. We've got 1, 4/3, 5/3, and 2. So we need to use the y values at those 4 x values. So let's go ahead and do that now. Our first trapezoid is going to be from 1 to 4/3. So I'm going to have 1 squared plus 4/3 squared, those are the y values, over 2. And then I have to multiply by a base of 1/3. Next, I'm going from 4/3 to 5/3. So that's going to be 4/3 squared plus 5/3 squared over 2 times a base of 1/3 again. And then finally, I've got 5/3 squared plus 2 squared over 2 times a base of 1/3. Now let's go through and simplify this a bit. This was a no calculator question. If you look at the answer choices, this is not necessarily going to be a walk in the park, so we have to do this carefully. So doing this first fraction, we've got 1 plus 16/9. And we have a 3 times 2 in the bottom, so that's 6 in the denominator. Up here we've got 16/9 plus 25/9 over 6. And here we've got 25/9 plus 4 over 6. Simplifying a little bit further, this is going to be 9/9 plus 16/9, so that's 25/9 over 6 gives us 25/54. Next, we've got 41 over 9 over 6, so 41 over 54. And then we've got, 25/9 plus, this will be 36/9, so that's 61/9 over 6, which is 61/54. There we go. So we have a denominator of 54, which seems to indicate answer choice D, but we better add up the numerators just to make sure there's nothing that reduces here. So taking a look here, we've got 25 and 41. Actually, I'm going to add the 41 and the 61 first. So that's going to be 102 plus 25 is 127. So 127/54. And the answer choices, there's nothing that this reduces to that's an answer choice. If you think about this, let's see. These are not both divisible by 3 because the digits here don't add up to a multiple of 3. And I don't think there's anything else you can really check for 54. They're not divisible by 2, so yeah, we should be good. Choice D. For this problem, we want a trapezoidal approximation of integral from 0 to 2 of f of x using these table values for f. So we've got 3 plus 3 over 2 times 1/2. And these are all equal subintervals, so we're going to be multiplying by 1/2 each time. Next, we've got 3 plus 5 over 2 times 1/2, 5 plus 8 over 2 times 1/2, and 8 plus 13 over 2 times 1/2. Now this was a calculator question, but you could do it without one. Notice that all of these denominators are going to be 4, and we're just essentially adding the numerators then all over 4. So we have 6 plus 8 plus 13 plus 21 all over 4. That's 14 27 plus another 21 is 48 over 4, which is 12, which gives us choice B.
For this problem, they're saying if the definite integral from 0 to 2 of e to the x squared dx is first approximated using two inscribed rectangles of equal width, and then approximated using the trapezoidal rule with n equals 2, so two trapezoids, they want to know the difference between those two approximations. So we basically need to approximate this twice and then subtract the answers. To help us with this, it would help to have a few values for this function from 0 to 2. Since they're asking for two rectangles and two trapezoids, I'm thinking using the x values 0, 1, and 2, those will give us our two rectangles or trapezoids. So let's plug those into the e to the x squared function. E to the 0 squared, that's just e to the 0, which is just 1. E to the 1 squared is just e. And then e to the 2 squared is really e to the 4th. So that'll just save us the trouble of plugging those in over and over again. Now, the way that this problem is worded, they said we have two inscribed rectangles. So what does that mean? Are they asking for LRAM, RRAM, MRAM? You know, what is that actually getting at? So if we have inscribed rectangles, well, we're going to need to know whether this function is increasing or decreasing. That's going to tell us whether the rectangles are under or over the function. E to the x squared, that is always increasing. As you plug in higher values, which you can see here, you're just going up. So since that is increasing on the interval in the problem, and really everywhere, frankly, and you know, we want the rectangles to be under the curve. We want them to underestimate the curve. That means we need LRAM. LRAM underestimates increasing functions. So that's how we're deciding to use LRAM for our first approximation. So for that, I need two rectangles. The first rectangle using LRAM, we have a base of 1 from 0 to 1, times we need to use the left value, which is going to be 1. So 1 times 1. Plus, our next rectangle, we have an interval of 1 there as well, from 1 to 2. And the left value this time is e. So plus 1 times e. Well, this is just 1 plus e. And let's go to Desmos just to get an exact-ish sort of value for this. So 1 plus e, that gives me, I'm just going to round it to 3 decimals, 3.718 and some change. But I can always cut and paste it off of Desmos if I need to. Okay, now for the trapezoidal rule, we basically need to do base 1 plus base 2 divided by 2 times the interval length. So for our first trapezoid, we've got 1 plus e over 2, and then times the interval length of 1. For the next trapezoid, we need e plus e to the 4th over 2 times 1. And let's plug all of that in Desmos. So I need a fraction, 1 plus e over 2, and I'm not going to worry about multiplying by 1 because I know what that's going to do, plus another fraction. We have e plus e exponent 4th power divided by 2, and this all comes out to about 30.517. They just wanted the difference between those two approximations. And notice that they actually have the individual answer there, 30.51 is one of the answer choices. That's a distractor there. We need to subtract 3.718 from that. And if we do that, let's see, 30.517 minus 3.718 approximately comes out to 26.80. I'm rounding to 2 decimals because that's what the answer choices have. So that allows me to pick answer choice D.
For number 12, they're saying a trapezoidal sum over-approximates some integral, and a right Riemann sum under-approximates the integral. Based off of this, we want to know which of the following could be the graph of y equals f of x. So the key here is, understanding which methods under or over-approximate which kinds of functions. We're going to start with the right Riemann sum. I think that's the easiest one to really understand. So since this under-approximated with RRAM, that means this must be a decreasing function because you're always hitting the bottom side first with that right endpoint of your rectangles. So we've got a decreasing function which narrows this down to choices A, C, and that's it actually. All these other ones are increasing. So it's between A and C. Now the chief difference between these is that one is concave up and the other is concave down. Well, this is where trapezoidal rule comes in. Trapezoidal rule over-approximates if something is concave up. Like take this choice A, for example. You try making a trapezoid by connecting things with concave up function, and you've got parts of the trapezoid that are above the curve. So since trapezoidal rule over-approximates concave up, that means it must be choice A for this one.